On the morning of September 1st, 1859, English astronomer Richard Carrington was sketching sunspots through dark filters. Around 11 a.m., he saw a sudden flash of intense white light from the area of the sunspots. The whole event lasted 5 minutes, but what followed about 17 hours later was even more remarkable. The Earth's magnetic field trembled as a massive solar storm hit our planet. This wasn't just any storm, it was a geomagnetic storm so strong that telegraph systems across Europe and North America went haywire. Operators received shocks, and machines worked even when unplugged. Auroras, usually seen in polar regions, dazzled skies as far south as Cuba and Hawaii, turning night into day. According to NOAA, gold miners in the Rocky Mountains woke up and made coffee, bacon and eggs at 1 a.m., thinking the sun had risen on a cloudy morning. This event, now known as the Carrington event, was the most powerful geomagnetic storm in recorded history, hinting at the sun's hidden power and showing us how vulnerable our world is to its celestial moods. Fast forward to today, 15 solar cycles later, and we stand on the brink of another solar spectacle, the upcoming premature solar maximum and the reversal of the sun's magnetic field. As the sun approaches the phase of its peak activity in its 11-year cycle, it promises increased solar flares, sunspots and coronal mass ejections. While we marvel at the potential for beautiful auroral displays, there's concern for our technologically dependent society, its impact on our health, and the warming of the oceans. The maximum also comes at a time around the Artemis mission, humanity's return to the moon, after more than half a century. So what will the upcoming solar maximum do to our planet in the coming months? What are the anomalies in this solar cycle that NASA is concerned about? Finally, and most importantly, will the upcoming phase of the sun's activity risk the life of the astronauts of the Artemis mission on the moon? Everything on Earth owes its existence to the sun. As our primary energy source, the sun might look the same every day from our vantage point, rising in the morning and setting at night, a cycle that has been constant throughout human history. Yet up close, the sun is a dynamic ball of plasma. It's covered in sunspots, flares, and other features like prominences and filaments that can outsize our planet. Essentially, the sun is a massive ball of hot gas that's always changing, but this change follows a pattern. On average, every 11 years, the sun undergoes a cycle of increased and decreased activity known as the solar cycle or Schwabe cycle. We are currently observing the 25th cycle of such activity since systematic records began in 1755. But how did scientists notice the sun's activity changes over time? The key to this discovery lies in sunspots. Sunspots are temporary dark areas on the sun's surface, looking darker because they are cooler than the surrounding areas. The temperature in the center of a sunspot is between 3,000 and 4,500 Kelvin, much cooler compared to the surrounding area's temperature of about 5,800 Kelvin. They are caused by intense magnetic activity and sometimes can be as big as Earth. When astronomers started to keep track of these sunspots regularly, they noticed a fascinating pattern. The number of sunspots went up and down over a cycle of about 11 years. They also observed changes in the size of sunspots, the area they covered on the sun, and where they were located. A solar cycle starts with a few sunspots, known as the solar minimum. Then, as more sunspots appear, it reaches a peak called the solar maximum. After this peak, the number of sunspots begins to drop. marking the end of the cycle. Another interesting pattern is where the sunspots appear. At the beginning of a cycle, sunspots show up at mid-latitudes on the sun. As the cycle progresses, they move closer to the equator. This movement creates a pattern that looks like a butterfly when plotted on a graph called the butterfly diagram. This diagram is a great way to visualize the solar cycle's regular pattern. For a long time, astronomers kept a record of solar activity by observing the behavior of sunspots alone. But as technology improved, they noticed two more things that changed over a solar cycle. The first was the solar magnetic field. The sun is a giant magnet with a north and a south pole. The sun's magnetism lies at the heart of its dynamic features. Astronomers found that the magnetic field goes through a complete reversal of polarity with each solar cycle. This means that the solar magnetic north becomes south, and the south becomes north. The pole reversal occurs around a solar maximum, marking the end of the maximum and the transition of the cycle to its minimum. And importantly, marking the cycle's midpoint. This phenomenon remains one of the most intriguing unsolved problems in solar physics, as we still don't understand why the magnetic field reverses polarity throughout the solar cycle. While the reason for polarity reversal remains a mystery, one feature of the sun may be playing a major role in this. The sun rotates in a non-uniform fashion, spinning at different speeds, at different latitudes. At the poles, it rotates slower than at the equator. This is called differential rotation. It is believed that the sun's rapid differential rotation causes the plasma to drag magnetic field lines around, causing them to get tangled and twisted as they eventually reach the surface and create sunspots. Sunspots and other instabilities weaken the field lines even more, reducing them to zero and giving them a chance to rearrange and reappear at the poles with opposite polarity. Even though polarity reversal is a regular and predictable event, it remains one of the most intriguing unsolved problems in solar physics. Another aspect of the sun that changes with the solar cycle is its overall activity, including solar wind, solar flares, and coronal mass ejections. This activity reaches its highest point at the solar maximum and its lowest at the solar minimum. Because of these findings, monitoring solar cycles now involves looking at solar activity and polarity reversal, in addition to counting sunspots. But does every solar cycle have the same intensity and last the same amount of time? Not quite. There have been solar cycles as short as 9 years, and as long as 14 years since we began observing the sun closely. This means the 11-year period is an average of how long it usually takes for the sun to go through its cycle of activity. Each solar cycle is also unique in how intense it is. This is measured by the total number of sunspots. Yet there have been unusual periods in the history of solar observation that left scientists puzzled. One such period is the Maunder minimum, from 1645 to 1715, when very few sunspots were seen, about 50 compared to the usual 40,000 to 50,000. This time of low solar activity coincided with the Little Ice Age, when the North Atlantic region experienced colder than normal temperatures. Another period, the Dalton minimum from 1790 to 1830, also saw fewer sunspots and was linked to lower global temperatures. This happened during solar cycles 4 through 7. Then there was the modern maximum, from 1933 to 2008, which had higher than usual solar activity starting around solar cycle 19. Now, we're in solar cycle 24, cycle 25, and it's a shocker. Based on past cycles, scientists thought this one would be mild. But so far, the Sun's activity is not what was expected, showing us once again how dynamic and unpredictable our star can be. The current solar cycle is proving to be more intense than previously anticipated and is reaching its peak earlier than expected. When this cycle began in December 2019, forecasts predicted a peak in July 2025 with around 115 sunspots. However, the NOAA's Space Weather Predictions Center has updated its prediction, now expecting the peak between January and October 2024, with an estimated 137 to 173 sunspots. This change in prediction underscores the dynamic nature of solar activity and its inherent unpredictability. Understanding the consequences of this increased intensity and early peak requires a closer look at X-class solar flares. Solar flares are powerful bursts of electromagnetic radiation from the Sun's atmosphere, triggered by the reconnection of strong magnetic fields. The Sun's complex magnetic field, which covers its interior, sometimes becomes twisted and distorted. When these magnetic fields stretch to the surface and reconnect, they release tremendous energy, resulting in a solar flare. Flares are ranked by their strength. B class is the smallest, followed by C, M, and then X, the most intense. C-class flares are generally too weak to affect Earth significantly. However, M-class flares can cause short-term radio blackouts at the poles and minor radiation storms, posing potential risks to astronauts. Each class is further divided into a scale from 1 to 9. The Carrington event in 1859 was associated with an X-class flare. Since the current solar cycle started, the first X-class solar flare occurred on July 3, 2021, leading to a substantial radio blackout. This event marked the beginning of a series of X-class flares that have since erupted from the Sun. In early 2022, a flare from the Sun was powerful enough to cause geomagnetic storms, resulting in the loss of 40 newly launched Starlink satellites. Then, on December 15, 2023, an X 2.8 flare disrupted radio communications on Earth for 2 hours. On New Year's Eve, the Sun unleashed an X5 flare. Adding to the surprises, on February 21st, there were 2 X-class solar flares that occurred 7 hours apart. To the astonishment of astronomers, another powerful X-class flare, classified as 6.3, was unleashed by the Sun within 24 hours of these occurrences. This has been the most powerful flare emitted by the Sun in over half a decade. All 3 flares disrupted radio communications on Earth. As the Sun's activity reaches its peak, scientists expect more frequent X-class flares. Now we come to a crucial question. Does solar activity contribute to the increase in Earth's temperature, thereby causing global warming? The answer to this question lies in this graph. This graph shows a relationship between solar activity and Earth's temperature since 1880 up until 2020. The red line shows global surface temperature changes, and the yellow line represents the Sun's energy received by the Earth in watts per square meter. The lighter lines show the yearly levels, while the heavier lines show the 11-year average trends. The graph tells us that the two follow the same trend up until the 1950s, but something changes after that. The paths of solar activity and temperature trends start to split apart. This divergence shows that solar activity alone can't be blamed for global warming. While it may have some influence, it's clear that it is not the only factor at play. High solar activity can potentially impact NASA's Artemis missions to the Moon. The guidelines for the Artemis mission are clear. Launches should steer clear of times close to solar storms. This caution is due to the energetic particles from solar storms that can harm electronic circuits and disrupt radio communication, which may make it difficult or even impossible to stay in contact with the spacecraft. However, there's a silver lining to high solar activity. It tends to decrease the amount of galactic and intergalactic cosmic rays, offering better protection for satellites against these harmful rays. So during periods of intense solar activity, satellites are less vulnerable to the damage caused by cosmic rays. On a more positive note, the solar maximum phase increases auroras, known as the northern lights or aurora borealis. These are stunning light displays created when the solar wind's charged particles collide with molecules in Earth's atmosphere. Viewing these colorful displays is an incredible experience. The best places to see the auroras include Canada, Alaska, Iceland, Norway, Sweden, Finland and Greenland, where they light up the night sky with breathtaking beauty. So as we prepare for the solar maximum, it reminds us that we are just a small part of a much bigger universe. It's a chance to reflect on our advancements and vulnerabilities, encouraging us to look beyond our daily lives and consider the bigger cosmic picture that connects us all. Recently, the James Webb Space Telescope discovered the farthest black hole ever, sitting at the edge of time. The discovery of this black hole seems to have solved one of the biggest puzzles in astronomy. If you missed this episode, be sure to catch up on the exciting discovery.